We are discussing embedding theorems, and yesterday let me recall the lemma of Galiardo. So we have that f1 fn belong to Ln minus 1 Rn minus 1, and you have xi hat is x1 xi minus 1 xi xn. You drop the ith coordinate, so this belongs to Rn minus 1. If x belongs to x equals x1 xn in Rn, then you define f of x is equal to f1 x1 hat fn xn hat. Then you have integral mod f dx over Rn is less than or equal to product I equals 1 to n of mod fi 0 n minus 1 r n minus 1. Okay, so this was Galiardo's lemma. We checked it in case 2 equal 2 and 3. 2 was just separation of variables, 3 was Cauchy-Schwarz inequality, and the general case follows by induction on n and using Helder inequality instead of Cauchy-Schwarz inequality. Now we are going to discuss the case p less than n. So we want to define 1 by p star equals 1 by p minus 1 by n. Okay, so this implies that of course that p star is greater than p. Okay, so now we have the important theorem. So theorem, landmark theorem. So this is called Sobolev inequality. Okay, so let 1 less than or equal to p less than n. P star, let p star be defined as above. Then there exists a constant c which depends only on p and n and strictly positive, such that for every u in W1p of Rn, we have mod u 0 p star Rn is less than or equal to some constant times mod u 1p Rn. Okay, so this is the Sobolev inequality. Okay, so proof, step 1. So let u belong to D of Rn, 1 less than or equal to I less than or equal to n. So you can write mod ux is less than or equal to integral minus infinity to infinity mod du by dxi x1 xi minus 1 t xi plus 1 xn dt, which I am going to define as fi of xi hat. Okay, so what have I done here? I have applied the fundamental theorem of calculus. Mod ux can be written as minus infinity to xn xi du by dxi of all this, because C infinity function compact support, so everything is fine. Now when I take modulus of that, then it's less than or equal to mod of this, and then I simply take, instead of xi I am putting a higher number, so I am going to take it to infinity, and so I get an inequality, and then this is now a function in everything except xi, and therefore I am going to call it fi of xi hat. Okay, therefore you have that, so this implies this you can do for each I, and therefore you get that mod ux to the power of n by n minus 1 is less than or equal to pi I equals 1 to n mod fx fi of xi hat power 1 by n minus 1. So I have just first I am taking for a product So I get mod ux power n less than equal to product f xi hat, and then I am taking n minus 1th root, so I have get this. So u has compact support, so this implies that du by dxi is integrable, and therefore you have implies for every 1 less than equal to I less than equal to n, you have that fi of xi hat mod fi to the 1 by n minus 1, it belongs to ln n minus 1 Rn minus 1, because if I raise it to the power n minus 1, then I get mod fi will be just this integral, and that can be, that is in ln minus 1, because then you will get the integral on whole of Rn. Okay, so therefore you have this, so we can apply Galiardo's lemma immediately. So by Galiardo we get that integral on Rn mod ux power n by n minus 1 dx is less than or equal to pi I equals 1 to n mod fi 0 1 Rn minus 1, because I am going to apply it to fi power 1 by n minus 1. So when I take the n minus 1 power, I will just get fi, integral fi, so that will give you the thing. But then I have to take the power of 1 by n minus 1, and therefore I will get here 1 by n minus 1 in the power. So I am taking the n minus 1 power of this, integrate, and then I have to take the 1 by n minus 1 power outside. Now if I take the n minus 1 power and integrate, I will just get the L1 norm, and then taking the 1 by n minus 1 power outside gives you this. So and that is equal to pi I equals 1 to n of mod du by dxi of 0 1 Rn now, and then power 1 by n minus 1 that remains, because when I integrate fi in Rn minus 1, and therefore that will give you du by dxi, because already in the definition of xi we have integrated with respect to xi, now we are integrating with respect to remaining variables, so you will get integral on Rn. Now if you look at n by n minus 1, this is nothing but 1 star, because what is 1? 1 by 1 star equals 1 by p minus 1 by n. So this is equal to n minus 1 by n, and therefore 1 star equals n by n minus 1. Okay, so this whatever you have here you is nothing but this. So this is nothing but mod u of 0 1 star Rn, okay, and it is, so I must take it to the power of n minus 1 by n on both sides. So I will get here pi is less than or equal to pi I equals 1 to n of mod du by dxi 0 1 Rn. Now here I have taken the n minus 1 nth power of this norm, so I have to take the n minus 1 by nth power, so I will get 1 by n in this side, okay. And now that is nothing but each of this is less than norm of mod u 1 1 Rn, and there are n of them, and I am taking nth root, so this is just less than mod 1 1 Rn. So this proves star when p equals 1. So what is star? So this is star. So when p equals 1, mod u 0 1 star Rn is less than c times mod u 1 1 Rn, and that's exactly what I have proved here. So we have proved it when p equals and u in d of R. So step 2. So now we assume that p is strictly bigger than 1 and less than n, and let u is in d of Rn and u not equal to 0, because if u is 0 the inequality is trivial. So let t be greater than or equal to 1 to be chosen we are not choosing it yet, we will choose it in a meantime. Okay. So consider mod u to the t minus 1 u. So this is of compact support, no problem, because u itself has compact support and is continuously differentiable, because you are taking t power t is bigger than 1, greater or equal to 1, and you are multiplying mod u to the t minus 1 u. So this such a function is always continuously differentiable, we know that. So and in fact you can write du by dxi of mod u to the t minus 1 u is nothing but t times mod u to the t minus 1 du by dxi. So this is simple elementary calculus which you can check for yourself. If you take fx going to mod x power t minus 1 x, that's a continuously differentiable function, and this will give you the derivative. Okay. So in step 1 we only used the fact that u was continuously differentiable. We didn't use any higher derivative, though it's a differentiable. We didn't use any of the higher derivatives and so on. So we can still apply. So we can apply step 1 to mod u to the t minus 1 u. So we apply that to the function. So what is mod u? 1 star is n by n minus 1. Okay. So if you are going to apply it to this function, so when you take modulus of this function, you get mod u power t, and then you are going to raise it to the power of n by n minus 1. So if you integrate, then you are going to get mod u to the 0 tn by n minus 1, that is the power to which you have raised Rn, but then you are taking the n minus 1 by n power outside, so there will be a t which comes here, which is not accounted for. So this will be the thing. So that is less than or equal to pi t times pi I equals 1 to n of mod u to the t minus 1 into du by dxi power 0 1 Rn power 1 by n. So this is exactly what we had here. So this is, we are using this fact. Now you apply Helder's inequality here. So Helder, so this is less than or equal to t times, so mod u to the t minus 1, I am going to apply p prime, and du by dxi I am going to take the LP norm. So you get mod u to the t minus 1, if I take p prime, so I will get 0 t minus 1 p prime Rn, okay, and then I am going to take the power of 1 by p prime, so there will be a t minus 1 power which is remaining in the top, okay, and then pi I equals 1 to n, okay, mod du by dxi 0 p Rn, the LP norm of the derivatives, and then of course the 1 by n is still there. Okay, so p prime 1 by p prime plus 1 by p equals 1. So this is the Hölder inequality which we have used. Okay, so now we choose t. So choose t such that we have something power t on the left hand side, something power t minus 1 on the left hand side. So it's natural, if you can cancel, then I will get 1. So we choose such that these two are the same. Tn by n minus 1 is equal to t minus 1 p dash. So that the same norm is taken on both sides. Tn by n minus 1 equals t minus 1 p dash. So you have n by n minus. So what does this mean? That means n by n minus 1 into 1 by p dash equals, so I am going to divide by t on the other side, 1 minus 1 by t. Or 1 by t is now equal to 1 minus n by n minus 1 into 1 minus 1 by p. P dash is 1 minus 1 by p. That is equal to, I am going to bring out the 1 by n minus 1 outside. Then I will have inside n minus 1 minus n plus n by p. So the n will get cancelled. You get n by p minus 1. Okay. So, and so this will imply that t is equal to n minus 1 by n by p minus 1. So t is equal to n minus 1 by n by p minus 1, which is equal to n minus 1 by n. I pull out the n, then 1 by p minus 1 by n is 1 by p star, and that is in the denominator. So this comes in the numerator. Okay. And this is non-negative since p is less than n. We already saw that. Okay. And p is greater or equal to 1. So p star is greater or equal to implies t is also greater or equal to 1. Because from this formula it falls, because you are taking something smaller than n in the denominator. So the denominator is smaller than numerator. So this will be greater or equal to 1. Okay. So therefore from this you have Tn by n minus 1. Tn by n minus 1 is p star. Therefore you have, from this inequality you have mod u 0 p star Rn power t less than or equal to t. T is n minus 1 by n p star into, now the power t minus 1, whatever you had here, this is the same as p star, and so and we've taken and cancelled them all and leaving you only with 1 on the left hand side. So and therefore you get this equality into mod u 1 p Rn, because each of these is less than or equal to mod u 1 p Rn, and there are n of them, and then you are taking 1 by n power, and therefore you get just less than mod 1 p Rn. So this proves star this with C p of n equal to n minus 1 by n into p star. Okay, and u is in D of R. So final step, step 3, you have, so star valid for all 1 less than or equal to p less than n, okay, and u is in D of Rn. So if u belongs to w1p of Rn, 1 less than or equal to p less than n, so there exists un in D of Rn, un converging to u in w1p of R. So by star, what do you get? Mod un minus um 0 p star Rn is less than or equal to C times mod un minus 1 p star Rn. and this goes to 0 because its un converges to u. So, this is Cauchy and therefore, this is also Cauchy. So, this implies that un Cauchy in LP star Rn implies some un converges to some v in LP star Rn. But un converges to u in LP of Rn. So, in both of these you will have a subsequence which goes pointwise almost everywhere, and so that should imply that u equals v, and that implies that v is in fact u belongs to LP star Rn. And now by passing to the limit in the inequality you have, so and you have mod un 0 p star Rn is less than or equal to c times mod un 1 p Rn, and therefore you get star, implies star, by passing to the limit as n tends to infinity. So, this proves the Sobolev embedding theorem completely. Okay. So, now we will see some corollaries of this thing. Corollary. So, let 1 less than or equal to p less than n, then W1p Rn is continuously included in LQ of Rn for all q belonging to p star. So, proof p obvious, p star proved in the Sobolev embedding theorem. So, we only want to look for q belonging to p star. So, let us take p less than q less than p star, then there exists an alpha belongs to 0 1, because then 1 by p star is less than 1 by q less than 1 by p. So, it can be written as a convex combination. So, there exists an alpha between 0 and 1 such that 1 by q equals alpha by p plus alpha minus 1 by p star, sorry 1 minus alpha, 1 by q equals alpha by p plus 1 minus alpha by p star. Okay. So, then what does this imply? This implies that mod u to the alpha q belongs to LP by alpha q of Rn. Because if I take the alpha q p by alpha q power of this, I will get mod u power p, which is finite, and p by alpha q because of this relationship is bigger or equal to 1. Okay. So, this implies that p by alpha q is greater or equal to 1, p star by 1 minus alpha q is also greater or equal to 1. Similarly, mod u to the 1 minus alpha p star 1 minus alpha q belongs to L p star by 1 minus alpha q of Rn, for the same reason, because u is in LP star, we know that, and therefore if I take p star by 1 minus alpha q, it belongs to LP star of Rn. So, and you also have q is equal to alpha q plus 1 minus alpha q, and so by Helder we get that mod u 0 q Rn, which is integral mod q, which I am going to split as alpha q and 1 minus alpha q, and 1 by alpha q plus 1 by alpha q plus 1 by 1 minus alpha q, sorry 1 by p by alpha q plus 1 by p star by 1 minus alpha q equal to 1. So we are going to use the Hölder inequality, and so for for alpha q I am going to use this. So this is nothing but is, so mod u power q is less than or equal to mod u of 0 p Rn, and then because there is an alpha trailing there, so this will give you an alpha, and mod u of 0 p star Rn 1 minus alpha. So just check the algebra, so you will get this. So if you get integral mod q is this. So I have taken 1 by q on both sides, and that will go away, and then there will only be an alpha left behind like this. Now by the generalized AMGM, so generalized AMGM inequality, this is less than or equal to alpha mod u 0 p Rn plus 1 minus alpha times mod u to the 0 p star Rn. This is the generalized arithmetic mean, geometric mean inequality. In fact, this is the first type of this you use when proving Hölder inequality itself. So that is the starting point. So that is less than or equal to alpha times mod u 0 p Rn plus 1 minus alpha times c times mod u 1 p Rn, that is by the Sobolev inequality. And so all that is less than some c1 times norm u 1 p R. Okay, so the inequality, so this proves that it is in any of these LP spaces. Okay. Next corollary, let omega be contained in Rn and 1 less than or equal to p strictly less than n. Then there exists a c greater than 0 such that for all u in w1p0 of omega, you have mod u 0 p star omega is less than or equal to c times mod u 1 p omega, and mod u 0 q omega less than or equal to c times norm u 1 p omega for all p less than q less than p star. Okay, and then in particular for all p less than or equal to q less than or equal to p star, we have w1p0 of omega is continuously embedded in LQ of omega because of these inequalities. Now if omega equals Rn plus, or if omega has bounded boundary and is of class C1, we have W1p omega is continuously embedded in LQ of omega for all p less than or equal to q less than or equal to p star. So we have from Rn we are coming to omega. So what is the proof of this is very simple. So if W1p0 of omega, if u is there, then you have u tilde extension by 0 belongs to W1p of Rn. So for u tilde you write down, we have these two inequalities, and then u tilde nothing happens outside omega, and therefore you have the inequalities for omega itself. Okay, so that gives you the proof. In case of omega equals Rn plus, or if it has bounded boundary and so on, then there exists a prolongation operator 1p of omega to W1p of Rn. So you apply the theorem mod pu 0 p star Rn is less than or equal to C times mod u, Pu 1 Prn. But what does it mean? Pu restricted to omega is u. So mod u 0 P star omega is again less than or equal to norm mod of Pu 0 P star Rn, which is less than to C times Pu 1 Prn, and P is a prolongation operator, so this is less than to C norm u 1 Prn. We can't say mod, we have to say norm 1 P omega, sorry. And therefore, now similarly you can do for the Q also. So the same argument you apply. So you use the prolongation operator, and therefore you will have results for all this. So you see, you prove results for Rn, and then you can prove for any of the domains where you have prolongation operators, or for W1 P0 in the same way.